Hello everyone, welcome back. So today we are going to start with the first multi-key FHE scheme, which is based on NTRU. Multi-key FHE based NTRU. Okay, so what is the plan? We are first going to see what is the NTRU crypto system, and then we'll form FHE based NTRU. Then at last we are going to see our MKFHE. Okay, so this is the plan. Before starting with this, uh, yeah, if you want to know something about NTRU, NTRU was introduced as a public key crypto system in the 90s. In 1998, it was introduced in 1998, and yeah, by Hofstein and Piper. Hofstein and Piper. Silverman. They have introduced the NTRU, first ring-based public key crypto system. It was first ring-based yeah. And for the FHE in 2011, there was a paper which shows that this NTRU schemes, it can be modified. It was modified by Stahel. Modified NTRU, okay, can actually used for FHE, and this was given in 2011 by Stahel and Stenfield. And the paper title was "Making NTRU as Secure as Worst Case Problem over Ideal Lattices." So after this paper in 2011, there was the paper this LTV 12. Lupe Stromer back in 2000, they had given a paper in 2012, FHE scheme based on the security. The security was based on RLWE and decision small polynomial ratio. So first let us see what is this. The security is based on RLWE and RLWE problem I have already discussed, and decisional small polynomial ratio, DSRP. So what is this DSRP assumption? Let us see. Oh, sorry, DSPR. It is DSPR, not RP. DSPR. this was given. First, suppose there is a ring R which is zx or x raised to n plus 1, or the polynomial, say any polynomial phi of x of degree n. This is similar to your ring LWE problem. So phi of x is of degree n. Let q belongs to z, be a prime integer and a distribution by a distribution over R. Okay, and let me define one more thing. RQ, what is RQ? That is R over QR. Then DSPR says that I am writing yeah. DSPR says it is hard to distinguish between these distribution, between these distribution. Okay, what is this distribution? The first one is polynomial u sampled uniformly at random from RQ. If you find any polynomial u. Okay, second says that polynomial h where h is equal to 2g f inverse over q. Notation for this means, that means modulo q, where for f is equal to 2f dash plus 1, and this f dash and g are sampled. F dash and g are sampled from the distribution. Okay, so you just have to distinguish. You will be given two polynomial, say u and say h. You have to just distinguish which of them is this h. See, h is given of this form 2g f inverse, where this f inverse, this f is of the form 2f dash plus 1, and see, you have to choose f such that it should be invertible in modulo q, otherwise this won't be able to done. Correct? Yeah, now let us, yeah, this was the DSPR assumption. Let us first give modified NTRU, which was given in 2011, as I told you. So let us first see what is this modified NTRU. Okay. Now ring R is equal to, I'm having zx by x raised to n plus 1, this is x, and n a power of 2, where n is a power of 2. Let q belongs to z, be a odd prime number. Prime integer you can say, or prime number, that is okay. And then you have to define the distribution, say chi b bounded distribution. B bounded means what? B bounded distribution over R, which means yeah, and this B should be very smaller than Q, which means, what is the meaning of B bounded? The magnitude of the coefficient, the magnitude of the coefficient of a polynomial sampled from chi is less than B. Is that clear? So what is B bounded distribution? That means the magnitude of the coefficient of a polynomial sampled from chi is less than B. And already B is very smaller than Q. Okay, so now let us see what is key generation, encryption, decryption. Key generation, sample f dash and g from chi and set f equal to 2f dash plus 1. Okay, just note that what is f modulo 2? It is 1. Okay, and you have to find a f such that it should be invertible, correct? Okay, and set h is equal to 2g f inverse modulo q. This is your h. And what is the output? Output, that means what is your secret key and public key? Your secret key is this f and public key is h. Okay, this, it was very simple. I am having two polynomial sample from this chi, and then find f equal to 2f dash plus 1 and check whether f inverse exists or not. Check whether f inverse exists. If not, then you have to again find some f dash such that this should be true, and then find h, which is 2g f inverse modulo q. And what is my secret key? This f is my secret key. And what is my public key? I am having this h as my public key. Okay, this was key generation. Let us see encryption. In encryption, what are the thing? I am having my message and by using public key. Okay, so for m belongs to 0 1, again sample s and e from chi and parse h is equal to pk. Okay, and what is the output? Your c is what? hs plus 2e plus m modulo q. This is your ciphertext, whatever you are having. See, first thing what I did, I sampled two polynomial s and e from this chi distribution, and by using my public key, I just multiply h into s plus 2 into this error polynomial plus this m. M is my message. This is the encryption. Decryption is very easy. For decryption, I am going to use my secret key. So cipher text and your secret key. This is the input for decryption. First thing is find the value, that is parse f, which is your secret key, and compute z equal to F into C modulo Q. I'll directly write Q here. Yeah. First thing is whatever your ciphertext is, multiply F to this. Multiply your secret key F. So you are getting this Z, and then get the value of your message. Get your message Z modulo 2. So mu is your message. I think I had written M here. So maybe I'll write M. We'll get back our message M. M equal to Z modulo 2. Correctness, decryption, that is correctness, works very well. You can quickly check, see what is your Z. Z is FC modulo Q. What is the value of C? It is HS plus 2E plus M. Correct? Modulo Q. What do you observe here? This is, what is H again? You know something about H? It is 2G F inverse. So it is F into 2G F inverse S plus 2E plus M. Correct? And he will be having here, this will be 2GS plus 2FE plus FM. Correct? This is what you are having modulo Q. This is the value of Z. Now if you take Z modulo 2, everything will go away, this will go away, this will go away, and what do you know? F modulo 2 is 1, as I had already mentioned. Correct? So if I take modulo 2, I'll be just remaining with M, my message. So it was very easy to check. Now this is true only if your distribution, that is the all the element, this part, this error term, this is only true if the error term is less than your key by 2, then only this decryption work, otherwise it will be failed, and that can be managed because of that B bounded definition. So I'll just write, because all elements F, G, S and E come from the distribution and B is less than, very small than Q, there is no reduction modulo Q. There is no reduction modulo Q. Correct? And if it is going well, then you have to maintain this, as I told you, this part. The error part should be less than Q by 2. Now let us see what is the multi-key FHE. How do you extend this with the multi-key? Okay. See, in the multi-key fully homomorphic setting, we have two ciphertext that encrypt different messages. Suppose I am having two messages, M1 and M2, and with different public keys, H1, H2. So I am having two things here, you can observe. Suppose first part is here, second part is here. He is having his secret key and public key pair. So keys, let me say, he is having his public key as H1, secret key as F1, and this guy is having his secret public key is H2. Keys, let me write public key comma secret key, and this guy is having F2, and he is the message here, he is M1, here it is M2. How do he encrypt? Encryption, it is very easy, as we have already discussed. So here he will get C1, which is equal to, say, H1 S1 plus 2E1 plus M1 modulo Q. See, I told you that to encrypt the message M1, I have to first find the S1 and E1 from the distribution, and then this is the encryption. Similarly, you can get C2, which is H2 S2 plus 2E2 plus M2 modulo Q. You are having C1 and C2, and you can easily calculate C1 plus C2 and C1 multiplied by C2. So this is encryption, and then say homomorphic addition. You just have to add, let me write C add is equal to C1 plus C2. Correct? Homomorphic multiplication. C, let me write just multiply C1 into C2. Correct? Now if you observe, if you are having C1 plus C2 here, and if you multiply, it will have all the term, say, for addition it is very easy. It will be H1 S1 plus H2 S2 plus 2 times E1 plus E2 plus M1 plus M2, correct? So again, this decryption is only possible if this part is less than your Q by 2, and everything is going modulo Q here. Okay, so you are having this new ciphertext, which is addition of two ciphertext. Yeah, and now if you see, if you multiply this C1 and C2, what do you get? You will be getting something H1 multiplied by something. See, H1 S1 will be multiplied to everyone, H2 S2, something like that. So H1 will be multiplied to something, plus H2 will be multiplied to something, plus 2 times the error term will be there, correct? So at last I'll be having M1 into M2 over Q. So these are the terms which will be present here. And how do you decrypt? See, if you observe in Multikey FHE, what happens? To decrypt something, you need both the keys, correct? So yeah, so if we simply add them and try to decrypt with the joint secret key. So what is my joint secret key? Joint secret key. Joint secret key is your F1 into F2. Okay, now let us try to decrypt C add. So how will you decrypt? Just what was the decryption? Multiply first this F into C add. Okay, so if you multiply F1 and F2 with C add, you observe, try to see that this H1 part, this will be taking your F1, take F2 outside here for the first one. I'll just write it for you, F1 F2, and what is your C add? H1 S1 plus H2 S2 plus 2 times E1 plus E2 plus M1 plus M2. This is what your question, your thing is. What you have to do, you just multiply the first term. It will be, for the first term I am keeping F2 here, I am writing F1 H1 S1. Okay, plus for the second term I am writing like that, F1 F2 H2 S2 plus other thing will be as it is. Okay, now what next? What do you observe? You know the value of H1, correct? What is the value of H1? It is 2G F inverse. Do you see your public key? How was your public key? It is 2G F inverse, correct? So in this case, since there are two parties, here your F1 will be 2G1 F1 inverse. Here F2 is 2G2 F2 inverse. Everything is modulo Q. Okay, so if you see, this will be F2 into F1 into 2G F1 inverse S1 plus F1 F2 2 into 2G, yeah, here it is G1, here it is G2, 2G2 F2 inverse S2 plus 2 E1 E2 E1 plus E2 plus M1 plus M2. Okay, what do you observe next? Here everybody, see, F1 inverse will get cancelled, F2 and F2 inverse will get cancelled, correct? What do you observe? This thing is 2 into the first term is your F2 G1 S1 plus here what I am having F1 G2 S2 plus E1 plus E2. This all the four term have this 2 common, so I am taking 2 outside plus M1 M2, correct? So this was your first step of decryption, that is you by using your combined, that is joint secret key, that is F1 is the secret key of the first guy, F2 is the secret key of the second guy. This can be done using multi-party computation. Okay, what we are doing, F1 into F2 multiplied with the ciphertext C add, and what do you observe? I am remaining with 2 into this plus your addition of the message. At last what you have to do, you have to take this modulo 2. If you take modulo 2, everything will go away here, this part will go away, and I'll be having just M1 plus M2. That will be your decryption. So at last F1 F2 C add, take modulo 2. If you take modulo 2, you will get your message M1 plus M2. That means I got the message whatever I wanted to compute. I wanted to compute addition of two messages. What I did, I just encrypted. See, there were two parties who do not trust each other. The first guy, but they want to compute the addition of their messages, M1 plus M2. They don't want to reveal these messages. So what they did, he encrypted his message. He encrypted his message with his public key and secret key. With his public key, with his public key, he encrypted his message. He made it as C1, and this guy, he encrypted his message and made it C2. Okay. Yeah. And then what happens, I wanted to compute addition, I just simply add them, and the decryption works with the joint secret key, correct? And same happens with the multiplication. If you observe, if you multiply, I told you this guy is having h1 into something plus h2 into something plus 2 into, so if you put the value of h1, it will be 2g f1 inverse. So f1 into f1 inverse will go over, so this guy will be having 2 inside, this guy will also have 2 inside, and here this guy is also having 2 inside, correct? So I can take 2 outside and I will be having an m1 into m2 here. So if I take modulo 2, I will get the message m1 into m2. So in this case, your product of the messages also you can compute with the joint secret key. See, everything is possible if your that error part, whatever I told you, except for the message, the error part should be less than q, less than your q by 2. Because in the previous one, this is the error part, correct, which is quite bigger. Error increases every time. Again, one more thing you need to note here. For one addition and multiplication, this simple approach seems to work. Okay, apart from being able to do the computation, this scheme also allows the user use the for multi-key. Suppose I am having n parties, then I can similarly give the secret key and public key for the n parties. They can decide their secret key and public key, and they can do that. Okay, but let us consider a situation. Consider a situation what happens when where we have three ciphertext. Okay, say C1, C2, C3. Okay, and what do I want to compute here? And this, again, they are encrypted with the secret key F1, F2, F3. These are the secret key they are having. Okay, so this message M1 is encrypted with the using your secret key F1. M2 is encrypted with the secret key F2 by, yeah, this is the secret key by using the public key. This is my secret key. Yeah, I should not write like this, otherwise you'll think that this is symmetric key encryption. No, this is not. Yeah. Now suppose we know that we can already we know that how to calculate this C1, C2 and C2, C3. For C1, C2, what do I require? I require this joint secret key as F1, F2, correct? And for C2, C3, what is the joint uh, secret key? It is F2, F3, correct? Yes. So with this, can we do that? Can we find a joint secret key for this C1, C2 plus C2, C3? What will be the joint secret key here? Because for this I am having F1, F2, for this I am having F2, F3. So if I combine both the ciphertext, what is the joint secret key for this? That is the question. Yes. Yeah. Can we do this? F1, F2, F3. This is the joint secret key for this. Because if you multiply this with the first guy, the first guy requires only F1 and F2. So F3 will be outside here. So F1, F2 will be multiplied. Anyway, if you take at last modulo 2, that is not going to have any trouble to me. Okay. And similarly, in the case of C2 into C3, this is okay. This is very nice. Okay. But for the addition, it was very nice. But what happens if you are having multiplication? See, now I am having, the question is C1, C2 into C2, C3. Then what is the joint secret key in that case? In that case, the joint secret key will be this one, F1, F2 square, F3. Because there is C2 two times. So in this case, you'll require this F2 square. But that is a problem. Do you see? Because your circuit need not be always addition. If you are having this type of circuit, then your keys depend on your circuit actually, which is a problem. So this shows that it is necessary to be aware of the circuit that was evaluated on the ciphertext. And additionally, the size of the key grows faster than just the number of different keys involved. Size of the keys goes very fast. So to solve this problem, the author need to use the key switching technique, which is also called relinearization technique. To solve this problem, authors used key switching, or also called as relinearization. from a paper which was given by Brakaski and Vaikunthanathan. In 2011, this paper was in 2011, where they had given the title was efficient fully homomorphic encryption. Yeah, okay. So what happens here, what they have suggested, but the author have suggested that give the evaluation key also, one more instead of just public key you have to give one more key, that is evaluation key. And evaluation key is added to the that means instead of just giving public key there will be one more key, that will be evaluation key, that is pseudo encryption of the power of 2 of the secret key. That means what is the evaluation key of F? It will be say HS plus 2E plus power of F multiplied by F. So this is your evaluation key, and your this S and E are the newly sampled one. Okay, and this is not the real encryption because we have defined decryption only for a binary message, correct? So this is not binary, so this is not the real encryption, that's why it is called pseudo encryption of that. Okay, so when the ciphertext encrypted under the set of keys, suppose the when the ciphertext is encrypted under the set of keys say F1 a set, it has say F11 say F1I F1K and one more set is there F2 which is having F2I F2J. Actually I should have written here F2J to F2 some L. Are multiplied. See, I am trying to make the same cases. Do you see in the previous one I was having two set of ciphertext. This ciphertext can be decrypted by this set of keys, that is F1 and F2, correct, and this ciphertext is decrypted by this set of keys, correct. So this is my set F1 here, this is my set F2 which is F2 F3. This is what I'm trying to see. In the case of addition there is no problem, I can find a joint secret key which is F1 F2 F3, but in the case of multiplication if I am having, then I am having this square term, and if you are having more then it will get changed. So I just wanted to get rid of this two. Can I still decrypt this using F1 F2 F3? then it will be very nice if I am still able to decrypt it with this just F1, F2, F3. That was the main idea. Okay. Yeah. So if they are multiplied, then what happens? The keys which are in intersection, the keys which are in F1 intersection F2 would appear the keys in, let me just write, keys in this would appear as a square in the new key. Correct? That means suppose F2 is repeated, then the combined secret key will be F1, F2 square, F3, which was the problem. Correct? So for each of those keys, the ciphertext is corrected. Ciphertext is corrected with evolution key. Such that power of this key goes down. In the new key. Okay. So more how does this happen? Let us see. Right, more precisely, the inner product is taken. Inner product is taken between the bit expansion of the ciphertext and each of the evaluation key. Evaluation keys. Okay. In our previous example, if you see, let us try to relate with our previous example. In our example, what is your seed as? Because in that case, I have to find the evolution key of F2, correct? What is the evolution key of F2? It will be just some HS plus 2E plus power of F2. Okay. So what is your corrected ciphertext? I am denoting it as seed as. Corrected ciphertext is what? It is bit decomposition of your C multiplied with EK F2. Right? That means inner product of these two people, modulo Q. So whatever ciphertext you are having and the intersection, you just have to do this. Now C dash can be decrypted with the key F1, F2, F3. That's why it is called relinearization, because I am making it linear. Earlier I required F1, F2 square F3, but now I just require F1, F2, F3. So this gives a multi-key FHE. This was the main idea. So now let us summarize what is this multi-key FHE scheme here. This gives the following multi-key FHE. Okay, the first thing is key generation, same as NTRU, correct? You just have to find your secret key, public key, and one more thing I require, that evaluation key, correct? I require EK also. What is this EK? It is some HS dash plus 2E dash plus power of F modulo Q. Okay, what is your secret key here? Your F. What is your public key? H, correct? And this is your key generation. For the encryption, same. What do you have to do? So let me just write it. This is FIHI. For every public, this is going to be different. FIHI for each party. Here also this HI and this SI dash, dash. Everything is depending on the party, correct? So to encrypt a message, say M with the public key PK, what is the entry? Same as your NTRU. What you have to do? You have to, your C will be HS plus 2E plus M modulo Q. This is your encryption. So this is your first cipher text. M1 will be there. Then you have to use H1 and say some distribution, whatever, S2 dash or something, S dash or something like that. These are randomly sampled. Not, they are not same. Okay, similarly C2 you can do, and so on. Each party will be encrypting with their plain text, with their public key, correct? And decryption, for decryption, as I told you, we require all the secret keys. So this is suppose I am having this cipher text. What do I have to do? Compute first Z. What is Z? This is F1 Fn multiplied by C modulo Q. Multiply all the Fi's with C, correct? And what is the output? Just take Z modulo 2. That will be your output. See, whatever the message is, and I have told you, because modulo 2 everything is 1. For the message which is encrypted by the first guy, everything other F2, F3, everything is going to vanish. F1 will be the first one which is multiplied to the F inverse part. Okay. Addition, for addition there was no problem. Eval addition, you just have to find C add as C1 plus C2, correct? Eval multiplication, there are some cases. Suppose there is two ciphertexts C1 which is having the secret key F1 which is encrypted under this, and say C2 which has this F2. Okay, and for each F1 the public key and encryption key is also given to you. for each of the set, correct? So what I have to check, I have to say C naught or C mult, which is C1 into C2 modulo. Okay, this is what I have to decrypt it. Earlier I was able to decrypt it by the F1 multiplied by the uh, product of this intersection part, correct? If it was not an intersection, then it was easy. So if you take F1 intersection F2, you have to get all the evaluation keys which are common, because that will be the only common part between them. See, F1 I am having, this will be having public keys and evaluation keys. F2 will be having, say, public keys, evaluation keys, correct? I just have to find the evaluation keys of all which are common. This guy also having public key 2, this guy is having public key 3, ek3, public key ek2. So what do you think the common part is? Public key 2 part is common, so evaluation key will be there. So in that case, what you have to do, set j is equal to L and find this Cj. Cj is bit of Cj minus 1 Ek Ekiij. That means what are the things repeated? We are going to, each time we are going to do that. We are going to multiply with the bit decomposition part, modulo q. Correct? Suppose I was having, for example, there are two ciphertexts. Say one I am having C1, C2, C3, and here I am having C2, C3, C4. So this can be decrypted. Here F1 is what? This will be F1, F2, F3. In here F2 is what? This will be F2, F3, F4. So to decrypt this, earlier what I have to do, I just have to F1, F2 square, F3 square, and then F4. This was the joint secret key in the earlier case. What I am going to do, I am going to multiply the ciphertext, the product of these two. I'm going to multiply with the evaluation key of F2 and evaluation key of F3. That will reduce your ciphertext into a new ciphertext which can be decrypted in just by F1, F2, F3, F4. This will be just enough for them if you multiply with the evaluation key of F2 and F3. Okay, so this gives you a fully homomorphic encryption scheme, multi-key fully homomorphic encryption scheme based NTRU. Okay, so in the next class we will see GSW FHE scheme, which is based on LWE problem. Okay, thank you.